because
he has pulled out a bag of Kool-Aid.
bag of Kool-Aid, yes. Now if you're listening, we've got this beaker into which I am dumping the products of nucleosynthesis ejected by massive stars. And you'll see the color of this beaker of water change to the shade of purple. It's great Kool-Aid. All right, so now the process continues. Some more stars. We just enrich the gas between the stars. And the gas coagulates into clouds. The clouds become unstable and form new stars. Okay, here they are. So now we've got another generation of stars. And notice the color is now different because the stars have been enriched by the previous generation of nucleosynthesis. Right? They've been enriched. So you see this light purple. And so there we are. There's a generation of stars that's been formed. Now, some of these stars are heavier than 8 times the mass of the sun. And they blow up. They're supernovae. Boom! Returning hydrogen, helium, and newly synthesized metals to the gas between the stars. Of course, let's add those nutrients again. Further enriching the gas between the stars, making it even more purple. And of course, the process continues, and we can form now out of this even more enriched material a new generation of stars. So let's examine what we've got here. First of all, we started off with a reservoir of gas which was clear. Look at it now. It's dark purple. It almost looks black. Okay? Because it's been so heavily enriched by the nucleosynthetic products of previous generations of stars. That's the gas. You'll also notice that we have 3 generations of stars. In a real galaxy, there'd be many more than that. And you can see that the first generation is clear because it wasn't enriched at all. The next one is kind of light purple, and the last generation is dark purple, right? So each successive generation of stars also becomes more enriched in heavy elements, carbon, nitrogen, oxygen, the metals. Now, a couple of observations we can make about this. Oops, I spilled my star stuff. We can make some observations. It's a useful sort of model for, this is a real model of the chemical evolution of the galaxy that I put into physical form. And it makes some predictions. Okay, so it first says, the model says that as the fraction of mass in the system, which is gaseous, goes down, the enrichment of the gas goes up. The concentration of Kool-Aid, in this case, goes up. So you would predict from this scenario that if you go and observe a galaxy where there is a lot of gas, then you wouldn't see it as much enriched. Okay? Where there's less gas, there's more enrichment. When there's more gas, there's less enrichment. Yeah. And I mean when there's more in a proportional sense. It's the fraction of the system that matters. Okay? So that's one thing. We can go and test that. And we've tested that, and we find indeed that's the case. So this is a prediction that has come true. But notice there's another rather profound observation one can make from these test tubes. And that is that there is a generation of stars here that is not enriched. Right? There's no sign of any heavy elements. So if that's the case, we should be able to go out and look for stars with no sign of enrichment. And people have done that for the Milky Way where it's possible. And sadly to say, killing of a great theory by a single ugly fact, there are no stars that have no metals. None have been found. At least we know that there's a deficiency in the stars which have no metals. And no one knows the reason why, although I could give you a hypothesis. You might say, well, given that single ugly fact, what use is what I just told you? Like, is it a total waste of time, this model? No, because we have learned a lot of things about the basics of chemical evolution. And in fact, by predicting something that's not come true, we have to look at the assumptions that we're making in this model to reevaluate what it is that we're doing that's leading to an incorrect result. And this is how you learn in science, right? You start out with something simple, and you're guided to something complicated only by necessity. And so there's something in this picture that is wrong, leading to the production of stars with no metals, or at least the existence of stars today with no metals, when in fact we don't find such stars. So if you want to ask me later, I can tell you what we think is causing this. But that's, in a nutshell, chemical evolution of galaxies.
Okay. Can I